Welcome everybody to the second day of our meeting. The first speaker is Tadeusz Januszkiewicz. Tadeusz is a full professor at the Institute of Mathematics of Polish Academy of Science and at Wrocław University. He is a member of Polish Academy of Science. He does research in geometry, in particular in geometric group theory. His results on cohomology of buildings are truly remarkable. He is also interested in toric geometry, in non-positive simplicial curvature, Kato spaces, and characteristic classes of flat boundaries. His work contains a number of great ideas and had a significant impact on geometry. He spoke at International Congress of Mathematicians in India in 2010. He received a number of grants and rewards for his work, the most prestigious being Banach Prize of the Polish Mathematical Society and the Prize of Prime Minister for outstanding research achievements. He is active in training young researchers. He had many PhD students, but not only. He has been collaborating also with Polish Children's Fund, which is an organization which supports talented high school students. Tadeusz, please, the floor is yours.
Okay. Thank you, Edma. On the screen, you see the outline of my talk. In addition to my slides, you might be interested in looking up an exercise sheet with Mateusz posted on a conference web page. Which place? For on-site participants. It's 10 problems which are somewhat related to what will happen during this hour. So my plan goes like this. But first of all, I will talk a little about convex polytopes, hoping that everybody knows what a convex polytope is, and it's a tangible object you can relate to. And then the best way to study convex polytopes, according to me, is to make it much more complicated by constructing a building from them. Buildings are interesting in their own right in many places. I probably won't tell you much about this, but my hope is that you will see at least one interesting example of a building at this talk. And then we'll do algebraic topology with those buildings. The buildings is a space with a group function. We will do equivariant algebraic topology, and I will briefly give you my version of what algebraic topology is, and then to make things even more complicated, we will mix this algebraic topology with functional analysis. But at the end of the day, we kind of give up on this complications, and we try to study the simplest possible notion of this L2 algebraic topology, which is a notion of dimension. So we are roughly here. We're roughly here. And then there's the question is, can we compute anything from those complex spaces that we are getting? And the answer is yes, sometimes. And I will show you a beautiful argument, which is mostly due to Jan de Mara. which shows that which shows very explicit computation, numbers of functions arising from the algebraic topology. And then come mysteries. Mysteries, I will be very brief on mysteries, not because there are few mysteries. I want to make them even more mysterious. So the references to this material, all of it is published. And the references are solo paper of Demara, who is probably part of this habilitation. It's called Thin Buildings. Whoever saw Demara understands that it's a very appropriate name. Then there is a very thick Davis book on Coxeter group. If you want to go into geometric group theory, this is an excellent place to start, because it deals with a simple family of groups, which is rich enough to give you a flavor of interesting questions in geometric group theory. And finally, there is, but finally, there's this paper which explains what I'm going to say and a lot more. But I don't think anyone wants to look at this paper, DJ Okuń, but Boris Okuń was important partner in this project. Okay. Convex polytope. Convex polytope. Everybody knows what a convex polytope is. Convex set is something which, for any 2 points in a convex set, you form an interval between them. Czarny z ciemnym. Czerwony is green. This is convexity conditions. And for us, it may be, we are interested only in polytopes, so in sort of finite part of convex set theory. And these have two definitions. One definition is that you take a bunch of points in Euclidean space, D, and you form the closest, the convex hull of this, which is the smallest convex set. So a bunch of vertices. The other definition is that a convex polytope can be presented as intersection of finitely many faces. Sometimes such an intersection doesn't have to be closed, doesn't have to be compact, but let's ignore this point. Okay. So these two definitions, in a precise sense, dual to each other, and they lead to two generic two concepts of genericity of a polytope. Okay? To simplicial polytopes and to simple polytopes. So simplicial polytopes is a polytope such that if you look at every face of this polytope, you will get the simplex, which is convex hull of basis vectors in R. Simple polytopes are duals, so they are intersection of a generic family of this HIs. And yeah, and how do they look like? Well, it's hard to say what their faces are, but locally they look like a product of R process. So simple polytope locally look like this, R plus to the power D. So an example of a simple polytope is a cube. An example of simplicial polytope, it's dual octahedron. The duality here is, say, on a combinatorial level, the vertices of the dual polytope correspond to dimension 1 faces, the boundary faces of the origin, and vice versa. And there's something in between. On the exercise sheet, you are asked to contemplate this question more. Now, what do I mean that these are generic things? See, if you take a cube and you perturb its vertices slightly, and then you form a convex hull. Do you get back the cube? Probably not, because if you take a square and perturb vertices slightly, this looks like this. And then this face, which used to be a square, becomes sum of two triangles. So there's some subdivision. So whenever you take a bunch of points and perturb them slightly, and then take a convex hull, most likely you get simplicial polytope. While with the second description, if you take a family of hyperplanes, perturb a simple one. Okay. Now, interesting question. What are the interesting questions about convex polytope? Lots of interesting questions. There are combinatorial questions. Maybe you can count the number of faces of codimension K. If you're in three space, you can look at the polytope. You can count the number of vertices, edges, and triangles, or cells. That's the same for higher dimensions. And the question is, what are the possible things arising like this? There are some restrictions. There are some interesting restrictions. Some of them are very algebraic topology. The other thing is that you can. By the way, from now on, my polytopes will be simple. If I want simplicial polytope, I will take this dual, right? And the dual is denoted like this. This is a dual of a simple polytope. And then it's a simplicial polytope, so it triangulates a boundary of the simplicial polytope of the sphere. So interesting question, who was first addressed and solved in dimension 3, when D is equal to 3 by Steinitz, is whether the relation between triangulation, abstract triangulation, maybe curvilinear triangulation of the sphere, and boundaries of this polytope. And then there are so-called realization spaces, namely, you might say, okay, I have a polytope like an octahedron with, and then I want to look at all possible octahedrons. In other words, I want to look at these vertices of the octahedron, here an octahedron, move them slightly, as long as it keeps the combinatorics of the octahedron. You get some topological space. This is very interesting topological space. It's called the realization space of a convex polytope. This is some. Convex polytopes are very simple and very interesting objects.
So could you say something more about this realization space? For example, how big is it? What is the dimension of this space?
The dimension of the space you can compute yourself. Because in a simplicial realization, what you do is you take a bunch of vertices. So it's a number of vertices, and then you freely move each one of them. There's a number, the dimension is dimension of the ambient space, D times the number of vertices.
Okay, thank you.
But the homotopy type is. Okay. I said something that I want to do algebraic topology, and convex polytopes are basically this, basically bolts, they're contractible. So there's no place to work for algebraic topologies, right? Everything is contractible. Contractible spaces have trivial homotopical invariant. No go, right? Okay. Wrong. So this is my first complication. I want to say that I can look at a convex polytope as an Orbi space. So in other words, I want to enrich the structure of this polytope or something I well understand. And then it turns out that algebraic topologists are in this. Right? So what's an Orbi space? Well, first of all, the idea of an Orbi space comes from tiles. If you want to say that you have some tile, some brick like P, the polytope, simple polytope, and then you stick it together and get some space tied with those bricks. If this space has symmetry, then you can divide the space by a group of symmetry, and you want to divide it so that the group is transitive on bricks. So after dividing by the symmetry, you get back P. In other words, you present your brick P as a quotient of certain topological space with a certain group function, which is proper, just fine stabilizer. This is general notion, very general notion. I like this notion because it mixes the concept of a group with the concept of the space. Sometimes it's called a complex of groups. And it's a general mathematical idea. You can mix spaces with other categories. Okay. Okay, so now, well, I want to be specific to my situation of a convex polytope, and I want to present my P as a quotient of certain space, which I'm going to construct by some group which acts on this with a quotient P. Okay. And the first, and there's an additional parameter Q here. Okay. So this parameter Q is just you will see what it is. It's a natural number for now. And my construction starts with the construction of W, of the group which will act on this B. The group is given in terms of generators and relations. Everybody knows how to do it. You have so many generators, and then you start multiplying them. But then you take into account some relations, simplified words. Okay. This is standard group theory. And my presentation of this group is fairly simple because it generators are just three-dimensional one faces of P. In other words, the vertices of P dual. And relations are that every generator, every phase raised to the power Q plus 1, that's where this Q parameter enters, is 1. And otherwise, there are no other relations unless faces F and G intersect, and then the generators come. So if you want, I'm taking a bunch of cyclic groups and I'm declaring them to be partially commutative system. Right?
So sorry, we have a choice in choosing this Q, or is it somehow defined in terms of P?
You see in my notation, the W depended on Q. It's always B of Q and W of Q.
Yes, but given P, one can choose two different Qs. Yes,
two different spaces, and it's actually important that there will be many Q, which we will consider.
Okay, thank
it's
you.
not just one. It's P and the family of this enrichment. P. Okay. Well, okay. Now, so these relations depends really on one skeleton of P dual. So it means that you just have to decide whether faces intersect or not. So that means that this method works the nicest for so-called flat polytope. And flat polytope is a polytope such as dual simplicial polytope is flat or complete, which means that every time you see a bunch of points which are connected by edges pairwise, then there's a simplex on those points. There are no empty simplexes. But there's one exception. It's a boundary of the simplex. For me, it's not a flat polytope, even though it doesn't matter what. Okay. So that observation that it works nicely for flat polytope means that we are really connecting to graph theory. Whenever you have a graph, simplicial graph, you can form its clique completion. Whenever you see pairwise joint points, it's part of simplex. So that gives you high dimensional object. And this is what was kind of restricting to flat polytopes, which means that we are studying click completions of them. Okay. And then we are on our way to define this B of Q. And for this, we have to observe that if we have a P, if we have Q, and we already constructed WQ, this group, then on a P, on a polytope P, simple polytope P, we have a map which goes from P to the subsets or to the subgroups of WQ. Okay? And the map is defined simply that you take a point of P and you look at the subgroup which is spanned by the generators corresponding to all faces containing. Okay? So here there's my best picture, which is I take for P, I take a pentagon, and then this red, white, and blue, red, green, and red. This colorful picture tells you what is the function S. Okay? So the blue point in the middle is not contained in any phase, so the corresponding group is trivial. Just one element. On the boundary, the green point goes to a subgroup spanned by F1, because it's a pentagon, it has 5 faces, so WQ is generated by 5 elements, F1, 2, and 5. So for example, this element here is presumably F3, and the corresponding group is generated by. And finally, at the vertices, you have they contain 2 guys. So the group is Z2, ZQ plus 1 squared. Any doubts how to generalize this to higher dimension?
But I have still a question. What is Q in this case?
Q is the number which is different for every participant in this room.
Ah, okay.
Everybody has its own Q, but for me, it's important that for you, this is our accessory parameter.
Okay.
Given P, for every Q, I perform this construction and see what happens. Okay?
There are also people on Zoom, so there
Right.
are even more queues. Since there are people on
I
Zoom.
don't think there are so many people on Zoom. Can Q be 0? Excellent question. I think it's maybe it's on the next slide. If it's on the next slide, it's really excellent question. There you go. Q can be, of course. Q can be any natural number, but when Q is 0, then the group W of Q is not very interesting. Because if Q is 0, then every generators, which are many, raised to power Q plus 1, which is 1, is 1. So the group is just one element group. But when Q is 1, this is a beautiful group, which is called right-angled Coxeter group. And in this case, you can have a lot more structures. For example, when you do this for Q equal, when you do this construction with a flat polytope, Q equal 1, you will get a tiling of a space which is homeomorphic to Euclidean space of certain function. This is not true for non-flat polytopes. But for flat polytopes, this is what you get. And it's not topology of these things, but rather geometry, which is interesting. Actually,
well, may we come back to the previous slide, because I think we have not defined yet BQ. I interrupted you. I asked for Q and.
And then there was another interesting question. Here's the definition of. So what you do is you take a WQ worth of copies of P, and you start gluing them together. And the thing is that you take a basic P, you take a generators corresponding to this phase. When you take an element in the group corresponding to the generator, and you stick together a copy of W of another P. Right? I'm tempted. Do I have somewhere? Do I have? Okay. Right. I can draw a picture on a board, but let's say that, you know, let's be as simple as possible. Let P be an interval. Okay. Give me Q. What's your Q? Yeah. 2. Okay. Then you take a group generated by 2 elements, left and right, such that cube of each is 1. Then what you take? You take a lot of copies of interval, and then you stick them together. 3 at each vertex here, 3 at each vertex there, and so on. Okay? So the result here will be that it's a 3, which every vertex of which meet 3 edges, 3 regular 3. And if your Q is 5, then this also be 3, but now the balance 6, right? Well, maybe.
No,
Okay.
I'm sorry, I'm lost. What is P1 and P2? I'm sorry, it's a stupid
P1
question, but
that's okay. I mean, so here in this definition, BQ is given in terms of the Cartesian product of P and W.
okay, so P1 is a point in P.
Yes.
Okay. So,
And W1 and W without anything, this is W2, of course, are 2 group elements. And if they differ on the right by an element of this subgroup, you identify.
but you may also switch the role of P1 and P2 and have S of P2, yes?
But see here, there's something which might say that doesn't matter.
Ah, P1 is equal P2. Okay. Okay. Sorry. Sorry.
No. This is, you know, don't be misled. This is 2 lines, but it's a kind of mantra which geometric group theories like to say. What this thing says is that there is a space on which the group W acts, and a quotient is a projection on the first factor of this. Right? This is the projection because I don't think I wrote it down on this page, but maybe on the other page there is a group action. Okay? So this product group acts, of course, on the second factor by translation on one or the other side, and the relation is preserved if you act on the right. This is best if you do this during exercise session. I mean, I can spend more time on explaining details of this construction, drawing you examples, but best done in the closer alone. Okay, so yeah, so now we have this group. Now, what you need really to understand is that there's a space tied with the copies of P and the group action down. And now we'll start doing simplification. First observation is that there's no loss in information passing from P to W to the space, to the group action. At least no homeomorphic or combinatorial information. And what we do is we follow this sequence of simplification steps that algebraic topologists like. What they like to do is they like to compute homology of a space. To do this, they take a space, X, nice space, like one of these spaces we constructed. They triangulate it. And then they look at simplices of dimension K, and they allow to add them formally. So this is the first step. You kind of linearize your space by allowing formal addition of space. But what remains from geometry is a boundary operator, because every simplex has a boundary. So there's a map from k-dimensional simplices to combinations of k-1 dimensions. That map lifts up to formal combination called boundary operator. There's a fine print, of course, because you have to worry about science and so on, but that's the basic. Simplex has a boundary, has a simplicial chains have a boundary operator. And the boundary of a boundary is 0. That thing forms chain complex. And of course, this chain complex, because the boundary of the boundary is 0, then this chain complex has homology, which is what is written next to the bottom. Of course, the simplicial chains highly depend on the triangulation. Of course, you change the triangulation, you subdivide triangulation, much bigger chain. The mystery or beauty is that nothing happens to homology. Homology is robust. And this is the main reason why we're interested. It does not, it's a very robust, very brutal environment, even though maybe more robust is Euler effect, which is also independent of triangulation of the space and given by some sort of, yeah, maybe we'll get back to Euler. But that's a first simplification. So you take a space X, linearize it, and take a robust part of this homological. Now, there's a second generation simplification, which goes like this. You take X, you convert it to the space with a group action, and then say X is finite simplicial complex. Okay? You go up some coverage. There is always, you know, if the group gamma. So in my choice, I took a fundamental group of loops. And this group acts on certain space, which is called universal cover effect. Every triangulation of X lifts up to the universal cover. When it lifts up to the universal cover, you have a chain complex of the universal cover of those lifted simplices. It's an infinite mass probably, but it's equivalent with respect to fundamental group action. Okay? Because equivalence means simply that the boundary commutes with the group action. Okay? So if you have a simplex here, you take its boundary, then you translate it, you take its boundary. The boundary is a translation of the boundary of here. Well, that's clear because everything is defined down below. Okay. Now, this is not so popular in elementary algebraic topology books, but this is very efficient. Take X, trade it for a space with a group action. In the first instance, it's a universal cover. And then you pass to its homology group. So this chain complex. But now there's additional algebraic structure on this chain complex, which is they are modules over the group. You can multiply elements in this complex by group, and you're doing formal sums. So it's really a module of a so-called group ring of a group. So the group ring, for those who don't know, are the finite formal combination with coefficients in Z of elements of a group. And you can multiply it by literally take one sum, take another sum, multiply in a group. So that's the second, and that's a simplification. In many cases, simplification, especially when this space here is simple. But It's a simplification maybe, but in general it's a mess because homology groups are Z gamma modules, and Z gamma modules algebraic are complicated. So you want to take something simple. And what you can do is you can try to take dimension or gamma dimensions or something. Now gamma dimensions are, there's a notion of dimension over any ring, not as commutative, and it's a zero level of algebraic plane theory. So that's this K0 gamma Z. That's where the dimension takes place, and this is too hard for me. It's too hard for me, so I want to simplify further. Okay, I simplify further. What's the best way to simplify? Complete. Now, Banach was famous because he observed that complete vector space, complete North vector space, are much easier than incomplete. Because you can take limits and you can perform lots of constructions. So this is what happens here. I say Z gamma were finally supported functional group. Formal linear computation, some things you can think of as function. And there's obvious norm. Every group element has norm one, and they are orthonormal. Okay, so I can go from the Z gamma to L2 gamma, just L2 summable function. Okay. It's a Hilbert space. All the Hilbert. The gamma is presumably countable group, so this is separate Hilbert space. That looks like a big simplification, right? There's Z gamma, which was the problem, and now we have one Hilbert space. Yeah, but gamma acts on this Hilbert space, so you do get unitary representation with gamma. So I traded Z gamma to regular representation of gamma, and there is very similar discussion for this module. This module are the functions on gamma, which are left, no, right, invariant under a finite subgroup F. Okay. So there are constant functions, constant on all costs. So there's still action of gamma. Okay. You can complete that. And now the point is that.
Sorry, I have a quick question. So F is chosen somehow, or F is chosen?
No, F is any finite. F stands for finite subgroup of gamma.
Yes, but it is fixed. Yes.
It is fixed.
Okay.
But think about your W. The W has lots and lots of finite subgroups, right? Corresponding to faces, vertices. And now I complicated things further to get into the functional analysis. But now I have a tremendous help from functional analysis, namely, I have a notion of dimension, which is called von Neumann dimension. And I don't want to explain to you how you define it in functional analysis terms, but here is a homological algebra description. You define dimension of gamma action of L2 of so this is called gamma dimension. Okay. Hilbert space is unique, but group action on this Hilbert space has to take into account. And the dimension depends on that group. So what do I know? I know that dimension of the space L2 over F of functions constant over cosets is 1 divided by cardinality of F. That's why it was a good idea to take F fine. And then it follows that dimension of L2 of gamma is 1. This is normalization, but it's not normalization. And then what happens is that homological algebra approach is that, okay, you define this function of certain module, certain gamma module, and then you look at you can extend it to kernels and co-kernels of any gamma Z gamma module map. So what I've done is that I say, suppose that K and L are in the form like one. Take any nice map commuting in the gamma action. Then I know how to define the gamma dimension of the kernel, which is gamma space. Gamma acts on the kernel. Gamma acts on the co-kernel. Okay. So I know how to extend this notion of the. Yeah.
Sorry, is this dimension somehow related to this type 2-1 von Neumann factors? Or?
Fine as a so group algebra von Neumann algebra of like the infinite group is of what type? 2-1?
It depends from the group, as far as I know. Infinite conjugacy classes group.
Best conjugacy class.
Yes, leads to factors.
But yeah, sometimes but all you need is the notion of a good trace, and on the group algebra there is a trace.
Okay.
Which is assigned to an element in the algebra value of the function of 1.
Okay, thank you.
Okay. So now we know what are the numbers we want to compute. Numbers we want to compute are the L2 Betty numbers of B gamma, B, EQ. EQ is a space on which WQ. And we take this dimension of those L2 cohomology spaces. Should I back up on this? Did I say exactly what L2 cohomology is? L2 cohomology is something like this: that you take a functions, L2 functions with copies of P. There's a notion of the boundary, just like in a simplicial. So the module are spanned by P's and by various faces of. These modules are all of the type. So if you take if you want to say C K of BQ. So what this is a, first of all, this is a completion, L2 completion of finite formal combinations of these guys. So here I should sum up over all k-dimensional faces of P. K-dimensional faces, simple polynomial. Maybe over all vertices, maybe on all edges, maybe on all faces also. But each of them is of the form L2 of WQ divided by one of this F. Because every face had a F. Because every face had stabilized. So we're talking about K face, you have to divide by K face. Okay. And now there's a notion of boundary which changes this into a complex. And right, you take a K face, you associate the boundary. Everything is W equivariant. And without any trouble, you can extend this this boundary operator to L2 completion. There are, of course, there are boundary operators. Okay, so now this is what that thing is. W acts, so you have a gamma dimension. So you know what it is, and the question is how you compute. Is it computable? It is relatively simple, maybe, because I took just dimension. I took very, very robust information. Okay, so the story how I compute this goes like this. First of all, you realize that the spaces BQ I constructed have much more symmetry than W. These are huge, uncountable groups. And the chamber stabilizer, the stabilizer of a copy of P in that group is compact. So this you can easily understand when you say for P, an interval, and then you have this regular tree, and you ask yourself, what is symmetry group of this regular tree? Oh my God, it's an enormous group. Because first of all, I can take it's clear that you can take one interval here, another one, and move it like so. Okay. And then you ask yourself, and what are the elements which are fixing this interval? Fixed. Independent fixed. So that gives you this compact group, like by flip, I mean automorphism, which does this, and say holds the left part alone, and then it rigidly. So I guess if this goes to that, then this goes to that. That's all, right? Anyway, you can flip at will everywhere on the tree. And it turns out that you can flip at will everywhere on the BQ. And why this group? Why this group fixing that thing is compact? Well, because that's next slide. But maybe if you fix interval here, you have a map from automorphic or the full automorphic group fixing Q, the automorphic group of certain ball of radius P. That group certainly is ball is compact. The maps are simplicial, so it's a finite group. So your fixator of this copy of interval has a maps the family of finite groups. Okay? And when you think about it, it's expressed as a limit of this family of finite. That's a beautiful problem. Okay, but I need this compact group. And now what the next step is that you observe that this chains, L2 chains, contain a subcomplex of things which are invariant under K. Of course. I mean, the content here is to say that things invariant under K form a subcomplex, a closed subcomplex. Now this subcomplex is nice, but there are some problems. Let me tell you. First of all, on this complex, before taking invariant part, you have two notions of dimension W dimension, but also automorphism group of B cubed R. And that gives you competing notion of dimension. No, it's the same dimension. Okay. In the case, yeah. Then there's a problem. The problem is this: that if you take invariant part, the automorphism of B don't add it. This is a serious problem. Mathematics. To say what? There's no group action. What do I do? What I do is that you see, and that's probably the model. Say that, well, the Hecke algebra. A Hecke algebra is a thing that quantum topologists like. But here, our Hecke algebra in context of building is something really, really simple. Namely, functions on W or functions on BQ is the same as invariant functions of the automorphism. Invariant on the left. This is trivial. Okay. Invariant subcomplex correspond to functions which are bi-invariant. Invariant over K on the left and invariant over K on the right. Those functions, you can compose them. You can convolve them. Functions with compact support, you can convolve them. That's the Hecke of the building BQ or the algomorphism of its buildings. And then once you discover it, what acts on this subcompass here, you have two competing dimensions to come. The Hecke dimension of this guy and the von Neumann dimension of this guy. The theorem is equal. They are equal. And now from this, the good news is that you can complicate things further. You can say, I can arrange so that Q was not only 0, 1, 2, 3, but Q can be any positive element. Why? Because first of all, you can reinterpret this space here as a Q-weighted L2 space on this. I don't see when you have finite support function on a building, you can push it down to this D1 to make it. Anyway, you can interpret that complex of some L2 spaces on something which is not dependent on Q, and Q enters only in the norm you're using. And the second step is that this Hecke algebra, which was abstractly given very simply, can be specifically given in terms of generators and relations, quadratic relations involving Q. And when you look at those relations, you realize that if you care for algebra of the group, Q can be anything, because in fact any complex number. So algebras are more flexible than groups, and that's good. And now you have this L2. This Q is any positive real number, and now you have a function from Q's to this, a function which takes Q and goes to this number, this real number, that's a function of Q. And so I have even more things to compute. So we do the computation for a small Q. We understand this is what happens. All these Bethe numbers are completely boring. They're 0, except one, except the 0, 1. Okay. In fact, at dimension 0, this Hilbert space is one-dimensional as a real dimensional space, but it's from the second dimensions with that number. It's one of the WQ. I need to explain what WQ is, but maybe, yeah. This is the gross series of this W1. And small means something precise. So yeah. Okay, I mean the WQ is an X. Okay, so you take this group W1 and because W comes with a set of generators, there's the natural length of element, shortest, more efficient representation in terms of them. And then you form this power series. And the sum of the W in W1 Q to W. That's a formal power series of a rational function. And it comes, evaluating this, it comes in first to alphabet. Happy? You should not be, because this is useless for our original thing. Convergence radius of a power series is always less than 1. So in this thing, Q is always less than 1. So there's no building at all. No BQ we construct, no space. It's covered by this one, right? Totally useless. Hello. Unless there's duality. And this is again, this is the model. Okay, what duality says is that there's a relation between this cohomology group of these buildings for Q and Q. It's a version of Poincaré method. And to compute Betty numbers for small q helps you to compute top dimensional. Well, okay, I mean, so this duality holds in general, no matter what q is. Okay? But in our applications, left-hand side is understood for small q. So the right-hand side, and it's zero everywhere except. So on the right-hand side, everything is zero except the top dimension. And you know what it is. And you know what it is. Because you just plug into the same font. Okay. So this is all except the mystery. So you know, this is my version of how mathematics look like. Take a problem, complicated. You cannot say anything about the more complicated problem. Simplify. You say something, but not what you want to say. So you complicate again. You cannot do anything. You simplify and so on. Sometimes this process terminates. So here, it's sort of terminated. But the last, yeah, I mean, I think the question to you should be, where should be the last step? At the bottom or at the top? Should you end up with complicated things, or should you end up with simple things? Okay. So what happens now is that this is the mystery part. The mystery part is that this computation that we had give you something for small q and for large q. What happens in the intermediate? And I don't know. And I think this is one of the most serious mathematical problems I have had. It has various phases, but one thing which I would love to see is that if you can say something about what happens in the range, then most likely we will get a new invariant, this Betty number, which are invariants of convex polytopes. Generally, new invariant. What we have now does not produce new invariant. Related to this function WQ, and it relates to the combinatorics convex polytopes well understood. But very good. So I think that's it. Thank you very much.
Okay, now questions.
If possible, I can.
Please.
So,
Marek.
yeah, Marek
Please, Marek, please.
Yeah, I am very happy to listen to such beautiful talk of Professor Januszkiewicz on building and nice cohomology. But as you know me, I like examples. So for me, I work sometimes with Professor Januszkiewicz on Coxeter groups, and then I understand. But building is like beautiful generalization. And my question is, when we work on Coxeter group, like permutation group, sign permutation, or some other dihedral group, and so on, we have nice interpretation that function what was on a recent not some transparent q to the length function, but that we consider as a function on group. But now we work on the building. So my question, if this has an interpretation in some representation theory, or maybe in physics, I like commutation relation, connection with Heisenberg group, or some other, can Tadeusz explain something about this on physical application? Because I never heard, but should be nice application, of course, that to the commutation relation and quantum physics, or recently even quantum computing. Anyway, so I think too many questions, but I think Tadeusz, Professor Januszkiewicz probably know this and can explain, not maybe now, but maybe during the school. So thank you very much once more, and thanks that I can see you and discuss.
It's good to see you in good health.
Okay, so please.
So I don't know
Let's
what
think
you're.
about permutation, group and that buildings. This is simplest or no? This is difficult.
Okay, let's
What's your-
allow Tadeusz to answer.
Okay, thank you.
So in case where first of all, our discussion was restricted to right angle build. The formulas and the results hold in more general. So from that point of view, it does make sense to look at finite groups. So I don't know if you want me to explain what is a building associated with a finite Coxeter group. It doesn't have this nice presentation of P. But there are buildings for finite groups that relate to linear groups. Or the Coxeter group that plays the role of Weil group of the corresponding of the Weil group. And this formula is known unconditionally. Unconditional, that is for all Q, and it doesn't need any functional analysis because finite groups leads to compact spaces. VQ is compact, right? And classical, so group theoretic part of this formula of Louis Solomon, maybe from the 50s. As soon as it discovered building, Solomon proved the result level. And a Hecke algebra part, so that the Q varying between varying over all numbers, it's not in the literature, but it's an exercise. Presumably. Maybe it's not in the master. So that's number one. Then Marek complains that
No, I don't complain.
Cicho. Marek complains that he understands Coxeter groups and he doesn't understand buildings. And I share his position. I think that my measure stick for judging whether theorem of about building is a nice geometric theorem is when it reduces the statement to the statement about the group W1, the Coxeter group associated. So in V series, such theorems would be like you have some theorem about cohomology of a homogeneous space of a compact group, and this cohomology is explained in terms of the Weil group of the group. Secretly, this group W1 is a Weil group of the automorphism group of the building. Okay? So he's right. The buildings are interesting, complicated objects, and the best way to understand it is through the Weil group that is constantly. Now about the quantum computation, let me quote a friend of mine. A long time ago, I had a fantastic project on generalizing some very classical concepts to much wider statement. And he was an expert on this classical concept. And I came to him and said, let's do it. And he said, I have so much trouble with this classical thing that I don't need any generalization. So that's my position about this. I think that there's enough of pure mathematics to be done without applications. Some applications are genuine application, useful application. No doubt at all. There's a lot of fake applications. So I don't want to get myself into any fake application, and I certainly don't want any of you to do it. So that's it. I have no comment on it.
Thank you, Tadek. Thank you very much. Thanks. I think-
Okay, any other questions? Maybe, please.
Okay, so you mentioned that the most interesting part is understanding this behavior for intermediate values of Q. Yes, so in concrete.
Most interesting, I don't know.
Okay,
It's
but still, in some simple examples, what are the possible values of Q which are difficult? For example, if you
One.
take something, one is
One,
difficult already. Okay, so one is something already
It's right in the middle of
right in the middle.
of the- and there's a famous conjecture which tells you what happens in this context for Q for one. And the two cohomology groups are all zero except in the middle dimension. Except so if your polytope is d-dimensional, then everything is zero except the middle. If D is odd, you are out of luck and everything is zero. If D is even, there's this one group which doesn't have to vanish. And I know its dimensions. It's one of W of Q.
Sorry, this is a conjecture, yes?
This conjecture, which is established for P of dimension up to 4. This is called Singer. And it's a part of more general, very interesting network of conjectures about aspherical manifolds, manifolds with universal covers. In fact, it's a very
And do you expect some deep, I don't know, maybe geometric reason why this dimension 4 appears in? So since you mentioned that for up to dimension 4 is
the Singer conjecture is most likely true everywhere. Dimension 4 is the artifact of the proof, and the proof is what goes in the proof is homological algebra passing from dimension 3 to 4, and then a result in dimension 3, which is hyperbolic geometry. On the one of the things that started first.
okay. Thank you.
Okay, any other questions? And people on Zoom? Okay, if not, I still have a short question. So you have a certain polytope P, you define many groups, P of Q.
Yeah.
So is it so that for given P, some specific Qs play the role? Or all of them play the role? All of them. So we do not, I mean, it would be a mistake to define just for one Q, Q equal 1 or something, because we lose information, yes?
Oh, we lose perspective. Information, I don't know. Maybe we don't lose information in the sense that if you give me one of this BP with W action, I know what P was. Then you give me Q and then I construct, or you give me Q prime and I go construct. So it's not a loss of information, but it's a loss of perspective. Because, for example, conjecturally, this functions, Q goes to Betty number, are piecewise rational. Okay, typically they look like 0, 0, 0, rational, 0, 0. So it's a good idea to have Q varying over the real numbers, continuous varying continuous.
Oh, okay.
So sorry, you said that those functions are piecewise rational. So these points of gluing are in this integer Q or not? No.
The first
Oh.
you should look at this theorem about small signal. See, this 1 over WQ is a rational function. And it jumps down to 0 at the convergence radius of this power.
Okay. Yeah. Thank you.
Okay, I think we may.
To ask you, does any one of you